So we are now at the point we get to talk about that second main topic of integration. But before we can get there, we want to talk about what antiderivatives are and what indefinite integration means. And then we're going to see a nice connection between these antiderivatives and the area underneath function. So pretty much we spend a large amount of time differentiating functions. Antiderivatives are going to reverse this process. So for our definition, we say a function capital F is called an antiderivative of little f on an interval I if, when you differentiate capital F, you land back at the function you started with. And this holds true for all x in your interval I. So basically the idea of this section is, given your derivative, can we find the function that we started with? So before we get to the rules, before we try to pick apart the pieces, let's try to work with a nice example. And so we'll think of the function f of x equals x squared. If we want to find that antiderivative, we can do that by thinking of our power rule. So normally when we're taking a derivative, the power gets brought down, we decrease it by 1. If I'm reversing that process, I need to compensate for the fact that the power was brought down, but I also need to bump up my power. So in the derivative, I reduced it to 2. When I bump it up, I better have a third degree power. So if I say f of x is 1/3 x cubed, so I've bumped up that power by 1, then I can check my answer. Because if I take the derivative of capital F, it would be 1/3, the 3 gets brought down, and it's decreased to x squared. 3 times 1/3 would cancel out, and I land back with x squared, which is exactly the function I started with. So what we can say is capital F being 1/3 x cubed is an antiderivative of x squared. Now realistically, I pick this function. The function g of x, which is 1/3 x cubed plus 18, is also an antiderivative of our function. Because if I take the derivative of g, derivative of 1/3 x cubed is still x squared, but the derivative of 18 is going to be 0, which still lands me back at the original function. So in fact, if I take this 1/3 x cubed and I add any constant c, then that's going to be an antiderivative of x squared because that constant will disappear with the derivative. So this is called our most general form for the antiderivative. Okay. So that is a theorem. If capital F is an antiderivative of little f on an interval I, then the most general antiderivative of little f on I is this capital F plus c, where c is an arbitrary constant. So pretty much you're going to find a function that works as an antiderivative, and then you tack on this plus c to give you the most general form. So essentially, you're really finding a family of functions, and that c is just going to shift it up or down. So they're basically vertical translations of each other. Okay. So with this new process, we have new terminology that we do want to go over. And we're going to kind of consider that with, again, the same function x squared. So its antiderivative would be capital F of x equaling 1/3 x cubed plus c. This is called the family of all antiderivatives of x squared. The value of c is going to be called our constant of integration, which we'll get to what integration means in a second. And capital F of x is also called the general solution of the differential equation where the derivative f prime is equal to x squared. So basically, you're finding a function whose derivative is x squared, hence differential equation. If you have to go on to that class, you're going to learn more complicated differential equations, but all it means is something involving the derivatives. Okay? So let's try a couple examples. Let's see if we can find the most general antiderivative of the following functions. And we're going to start with the function secant squared. So I want to find a function whose derivative is secant squared. So I need to go back into my book of tools, and if I think about my trig functions, if I let f of x be tangent of x, then the derivative of tangent is going to be secant squared. So the most general antiderivative we have is capital F of x equals tangent of x plus c. If we move on to g of t being 21t to the 6th, I want to find a function whose derivative is 21t to the 6th. So I know I need a 7th power because the 7 would get brought down and decreased to 6. So we're going to say g of t equals 3t to the 7th. Why do we pick that? Because when the 7 gets brought down in the derivative to the front, 7 times 3 will give us 21. So g prime of t would be 3 times 7t to the 6th, which is exactly 21t to the 6th. So the most general antiderivative we have is 3t to the 7th plus c. Okay. So let's kind of in general see if we can figure out if I have x to a power, but not including the case when n equals -1. So basically 1 over x we're ignoring for right now. We'll take care of that in later chapters. And again, here we're going to keep this power rule in our mind. So I need to bump up the power, and if I kind of think of what I did in this case, we had 21t to the 6th. It got bumped up and went to 21t to the 7th, and we divide it by 7. So we divide by that new power instead of multiplying by it. So what we can do is if we let h of x be, we bump that power up by 1 and divide by the new power. Then when I go to take the derivative of this expression, we bring the power down, the n plus 1 gets decreased by 1, so it becomes the nth power, and then we have that n plus 1 in the bottom. So ultimately, those would cancel out and land us right back to where we started. So if I have x to the n, the most general antiderivative is going to be x to the n plus 1 divided by n plus 1 plus c. And you can see now kind of why n equals 1 doesn't work, or n equals -1 doesn't work. That would cause you to divide by 0. So let's change the terminology slightly. Let's find the general solution to the differential equation. But remember, this dy dx is really just saying y prime is equal to 8x cubed. So I'm trying to find a function whose derivative is 8x cubed. And so doing this same process, my power was lost by 1. So I want an x to the 4th. And I want to compensate for the fact that the 4 gets brought down by dividing by 4. So 8 over 4 will give us 2x to the 4th, and then we add that constant of integration, c. And the nice thing is we can always check our answer by taking a derivative. Derivative of 2x to the 4th would be 2 times 4x cubed. Derivative of a constant is 0, so indeed we do end up exactly where we started. Okay. Let's try a second one. We've got dr dt is 3t to the 4 over 3. Same process again. I want to go ahead and I'm going to keep that 3 as is. I'm going to take that power and I'm going to bump it up by 1 because I lose 1 in the derivative. And based on what we did from the last example, we have to divide by the new power and then add on our plus c. So if you do 4/3 plus 1, it's 7 over 3. So this is equal to 3t to the 7 over 3 divided by 7 over 3 plus c. And then when you're dividing by a fraction, it's the same thing as multiplying by its reciprocal. And so 3 times 3 over 7 would give you 9 over 7 t to the 7 over 3 plus c. And again, we can always check. So if I take the derivative of this expression, the 9 over 7 stays out front. I bring the power down, so 7 over 3, and I decrease the power by 1 to give us t to the 4/3. And then we add our 0. And then we've got some simplification. The 7 over 7 cancels. We've got 3 that goes into 9 3 times. Indeed, this ends up giving us 3t to the 4 over 3. So again, I land right back to where I started. So I know I have found the correct antiderivative or solution to this equation. So now we can talk about what this indefinite integral is, knowing that I've used the word constant of integration for this value of c. And basically this process, going back up a little bit, starting with a function and calling its antiderivative capital of that letter is really tedious, because what if I need to take another antiderivative? I don't have a capital version of capital G. So this notation is kind of poor, and we have a different way to talk about how to take an antiderivative. Just like we have this prime notation and this d over dx to indicate take a derivative, the notation where you have this kind of s-looking thing with the function and with this variable at the end, this is traditionally used for the antiderivative of f. And this is what's called an indefinite integral. So there's kind of key pieces to what each of these end up meaning. So this sign is our integral sign. It looks like an S because you're going to see it kind of stands for sum in the very next section. And then this thing at the end is basically telling you what you're taking an antiderivative with respect to. So if we write this notation, the integral of f of x dx equaling something just means that if I take the derivative of this function, I land exactly back to the function I started with. So capital F prime is exactly the function on the inside. So this indefinite integral is going to result in a function, okay? So this is going to be the notation we use to indicate take an antiderivative. But ultimately, integration, antiderivatives are the inverse of differentiation. And then likewise, if I have a derivative, its inverse is going to be integration. So basically, there's a really strong connection between differentiation and anti-differentiation / integration. So from all of our normal differentiation rules, we can actually find the integration rules. So we've got a little table we're going to go through with all the different derivative rules and how they translate to finding the antiderivative. So first and foremost, if we take the derivative of a constant, we get 0. So if I want to take the integral or antiderivative of 0, I'm going to end up with a constant. So basically, I'm starting on this side and taking the antiderivative of this. It's getting rid of the fact that I took this derivative over here. Okay. We know if we take the derivative of some constant times x, like the derivative of 2x is 2, you just get the constant in return. So if I integrate a constant, I'm going to get a constant times x plus this coefficient of c. Because again, derivative of kx is k, derivative of c is 0. So the derivative of this quantity is exactly k. Okay. Now, if I do the derivative of a constant times a function, remember that constant pops out and I just take the derivative of everything left over. So the same kind of thing happens for antiderivatives. If I'm integrating a constant times a function, you can pop the constant out and find the antiderivative of the function that's left over. If we go ahead and take the derivative of the sum of two functions, you take the derivative of each individually. So same thing happens if I want the antiderivative of the sum of two functions, I take the antiderivative of each individually. And likewise, if you go ahead and do subtraction, same thing ends up holding. Then we know the derivative of x to the n is you decrease that power by 1 and you bring down the n. So if I'm reversing this and I'm finding the antiderivative of x to the n, you're going to bump up the power, divide by the new power, and then add your constant of integration. But this only works if you don't have 1 over x. So that's something we're going to need later. Then if we go to our trig functions, the derivative of sine of x is cosine of x. So if I integrate cosine, I'm going to land back to sine because the derivative of sine is cosine. If I take the derivative of cosine of x, it's negative sine of x. So if I'm just dealing with sine of x as an antiderivative, I know a minus gets introduced from cosine. So the antiderivative of sine of x is negative cosine of x, because when I take this derivative, the minus will cancel and end up with positive like I have on the left-hand side. And then again, we tack on the plus c. We know the derivative of tangent of x is secant squared. So if I integrate secant squared, I land right back at tangent plus that constant of integration. If I take the derivative of the secant function, it's secant of x times tangent of x. So if I integrate secant of x times tangent of x, I land right back at the secant function. For cotangent, remember its derivative is negative cosecant squared. So if I'm missing that negative, the antiderivative is going to have that minus attached. So again, the minus will cancel and land me back at cosecant squared when I take a derivative. And then likewise, the derivative of cosecant is negative cosecant times cotangent. So if I go ahead and integrate cosecant times cotangent, the antiderivative is going to deal with the cosecant function, but I'm missing that minus over here, so the antiderivative keeps it connected. Okay. And then again, we don't know what happens to the integral of 1 over x just yet. So you got to be really careful at this stage. You do not know what that is. We are going to go over that soon, because the next chapter is when we start getting into some transcendental functions like the exponential and logarithmic, and you're going to see it pertains there. Okay. The other thing you have to keep kind of an eye on is we adopt kind of the convention that when we have these formulas for an indefinite integral, it only makes sense on a particular interval. Sometimes it works no matter the value of x, but it doesn't always happen that way. So for example, think of the integral of 1 over x to the 4th dx. That's really just reversing the power rule, because this is like x to the negative 4. So I bump up that power by 1, divide by the new power, and add that plus c. So if I simplified it, it would be negative 1 over 3x cubed plus c. If you think of this function, it's undefined at 0. So we have kind of this understanding this only works when x isn't equal to 0. So on that interval from negative infinity to 0, 0 to infinity. It doesn't make sense at 0 itself. So let's try some examples. Let's find the most general indefinite integral, which basically means find the antiderivative. Again, this is the thing I want to find the antiderivative of. This dx is just telling me the variable. If you have to go on to Calc 2 or Calc 3 is really where you're going to see multiple variables. So you want to make sure you are writing these dx's over and over, because they do have a meaning. So what I need to do is kind of apply one of my formulas, but right now none of these are in the form x to a power. So what we can do is remember the square root is like a 1/2 power. So I'm taking x cubed, raising that to the 1/2. Likewise, cube root is 1/3 power. So that's x squared to the 1/3. And I want to keep writing that dx because this is kind of ending my integral. So this is the same thing as x to the 3/2 when you multiply those powers, plus x to the 2/3 on the inside. And we're finding the antiderivative with respect to x. So I can go ahead and take the antiderivative of both of these individually. So we go ahead, bump the power up by 1. So 3/2 plus 1 would be 5/2. And I want to divide by the new power. Same thing here. I'm going to bump up the power by 1. 2/3 plus 1 would be 5/3. So I divide by the new power and add c. And then anytime you're dividing by a fraction, it's the same thing as multiplying by the reciprocal. So dividing by 5/2 is multiplying by 2/5. And likewise, dividing by 5/3, multiplying by 3/5. And we add that constant of integration. So again, if you want to check yourself, you can go ahead and take the derivative, and you should land back to here really is going to be where you see it, which you then can manipulate into one of these other expressions. Okay. Now for this one, unfortunately, off the top of my head, I can't think of a function that has the product of two things as its derivative. So I've got to do a little bit work for this one, and we'll go ahead and distribute the secant to both pieces. So secant times secant would give us secant squared. Secant times tangent is exactly that. And I'm finding my antiderivative with respect to t, so that's my variable. So I need a function whose derivative is secant squared, which is our tangent function, and a function whose derivative is secant times tangent is our secant function. So the first piece would integrate to tangent of t, second piece integrates to secant of t, and then we go ahead and add that plus c. Okay. Now the last thing we're going to do is basically we can possibly have a condition that allows us to find this constant of integration. Because remember, it's basically shifted that same function up or down however many places. So if we happen to know a point that the function has to pass through, we can solve for the value of c in the antiderivative. Okay? So let's try to solve this differential equation. The derivative of my function is 7x plus 3. And when I plug 0 into my function, I better go through -4. So my point 0, -4 better be on this graph of my solution. So first and foremost, what I want to do is I want to find that antiderivative. If I deal with the 7x first, we go ahead and bump that power up. So it'd be x squared, divide by the new power. Antiderivative of 3 would be 3x, and then we tack on that plus c. So this is the most general solution to the equation. Now, using that particular point they give us, we get the following. If I plug 0 into this expression, that would give me 7 over 2 times 0 squared plus 3 times 0 plus c. Well, this better have an output of -4. So what this tells me is that c is indeed equal to -4. Okay, because this thing has to equal -4. Right? So ultimately, the function we're dealing with is 7 over 2 x squared plus 3x minus 4. Let's try a second one. We're given the second derivative is 3 sine of x, and we know a point the first derivative passes through and a point the function passes through. So before I even get to my original function, if I take one antiderivative, that gives me the first derivative. So I need to find the integral of 3 sine of x, and that would be -3 cosine of x. And that's since if I take the derivative of this expression, that negative is going to cancel, and its derivative will be +3 sine of x. And now we can use this piece of information to help us find the value of c. So what we do is we plug 0 into this expression, and that would give us -3 cosine of 0 plus c. Well, cosine of 0 is 1, so that's -3 plus c. This better equals 6 because f prime of 0 is 6. And really just adding that 3 over gives us that c has to equal 9. So right now what we know is our function f prime is -3 cosine of x plus 9. Okay? If I take another antiderivative, that's going to land me back at my function. So the antiderivative of f prime is f. If I go ahead and find the antiderivative of -3 cosine of x, that's -3 sine of x. Antiderivative of 9 is 9x. and I need to add a constant of integration, I'm going to use a different variable than c because I just used that above. And now again, I know that if I plug in 0 into my function, it better give me an output of 3. So we're going to use that piece of information to find the value of d. So if I plug 0 in, that'll be negative 3 sine of 0 plus 9 times 0 plus d. Well, if you go ahead and simplify that, sine of 0 is 0, 9 times 0 is 0, plus d, this better equal 3. So immediately I find the value of this constant has to be 3. So the function that satisfies all of these criteria is negative 3 sine of x plus 9 of x plus d, which is 3.